To determine the order of the reaction with respect to each reactant, we need to find two experiments where the reactant we're interested in has a changing concentration and the other reactants do not. So if we look at experiments 1 and 2, where only Br is being doubled, the other two concentrations are staying constant, we see an increase in the rate from about 6 times 10 to the negative 5 to 12 times 10 to the negative 5, suggesting when the concentration is doubled, the rate is doubled. This is indicative of, no, hold on a second. No, the rate stays constant at 5.7 times 10 to the negative 5. So because it stays constant, this is representative of 0th order. Now let's look at experiments 1 and 3. When we look at experiments 1 and 3, the change in concentration is that of H3O+, where the Br2 stays at 0.05 and the acetone stays at 0.3. So when we only double the concentration of H3O+, here is where we see about a doubling of the rate, about 6 going to 12. And this is representative of first order. If what we do to the concentration, we do to the rate, we double the concentration, we double the rate, we half the concentration, we half the rate. This is representative of first order. So it's first order with respect to H3O+, 0 order with respect to Br2. The last one's going to be a little bit more complicated. We don't see a simple doubling of the concentration of acetone. So let's look at experiments 1 and 4. In experiments 1 and 4, the concentrations of Br2 and H3O+ are all 0.05. The only changing concentration is acetone, going from 0.3 to 0.04. So what we can do is take a ratio of two rate laws. For experiment 1, the rate is 5.7 times 10 to the negative 5. We'll set that equal to K multiplied by the acetone concentration raised to its unknown order, multiplied by the bromine concentration raised to 0, multiplied by the H3O+ concentration raised to 1 because it's first order. We'll then divide by the data found in experiment 4, where we'll take the rate of experiment 4, set it equal to K, multiplied by the concentration of acetone raised to the X, multiplied by the bromine to the 0, and the H3O+ to the 1. The K's cancel, and these concentrations cancel. So we end up with 0.75 being equal to, this ratio is also 0.75 raised to the X, so X is 1. Thus it must be first order with respect to acetone. So the rate law then will be rate is equal to K multiplied by the acetone concentration raised to the 1, the bromine concentration raised to the 0, and the hydronium concentration raised to the 1. If we rearrange that equation, then we can solve for K, where K is equal to rate divided by the acetone concentration raised to the 1, bromine concentration raised to the 0, and hydronium raised to the 1. So in theory, you should be able to take the data for any of these experiments and you'll calculate the same K value. It doesn't ask you to calculate the average K value, it just wants a numerical value for K. So I took experiment 1 data and I got 0.038. I then took another experiment data and got 0.004, In the other one it was 0.003. So I'm just going to say to one significant figure it's 0.004. And the units are 1 over molarity second because it's second order overall. And when it's second order overall, the units on the rate constant are 1 over molarity time. Last of all, it wants you to calculate the rate when given particular concentrations. So the rate will be equal to our K value, which we determined to be 0.004, 1 over molarity second, multiplied by the acetone concentration. Now let's see, I'm going to do the hydronium concentration raised to the 1 multiplied by the acetone concentration raised to the 1, and then the bromine concentration raised to the 0, which is just 1, so we don't even need to include it. So the rate then will be equal to 2 times 10 to the negative 5, 1 over molar seconds, which is very representative of the rates we were getting with the other concentrations.